Talk about valence bond theory, that is abbreviated as VBT. Valence bond theory was presented by Hitler and London in 1923. This theory utilizes the concept of wave mechanical model or quantum mechanical model of an atom. According to this model, the electrons are waves which are represented by psi, and these are residing in the orbitals where probability of finding the electron is maximum. The regions around the nucleus of an atom where probability of finding the electron is maximum, about 95%, is regarded as the orbital. According to quantum mechanical model, the electronic wave functions psi reside in orbitals. So let's talk about the postulates of VBT, on which postulates the VBT is based upon. The very first postulate of VBT is half-filled atomic orbitals s, p, d and f overlap and result in molecular orbitals sigma and pi. The s, p, d and f, if they are half-filled, they overlap and result sigma and pi molecular orbitals. For the effective overlapping of the orbitals, these orbitals must be in plane, they have same sign, and they are symmetrical. The two orbitals can result in effective overlapping if they are in one plane and they have the same sign. For example, this is a p orbital and this is the plus lobe and minus lobe. That is going to overlap with the another p orbital. If two p orbitals have same lobes in front of each other, the lobes with same signs in front of each other, they will result in bonding. Moreover, you can see that these orbitals are in one plane along, you can say, x-axis. Then these orbitals can overlap. If one orbital is along x-axis and other is along y-axis, they will not result in effective overlapping and the bond will not form. So for the formation of a bond, two orbitals must be in plane, have same sign and symmetrical. If these orbitals overlap, these are filled with the electrons, and the filling of electrons must satisfy Aufbau principle, Pauli exclusion principle and Horn's rule. The extent of overlapping must be less than 50%. The fourth postulate is extent of overlapping must be less than 50%. If the overlapping extent greater than 50% result, there will be the nuclear repulsion and the molecule will become unstable. So the extent of overlapping for two orbitals must be less than 50%. So these are the postulates upon which the VBT is based. The first one is the atomic orbitals must be half-filled in order to result a bond. Secondly, these orbitals must be in plane, have same sign and symmetrical. Third postulate is after the overlapping, the electrons are filled in the orbitals according to Aufbau, Pauli exclusion and Horn's rule. The orbitals must not exceed their extent of overlapping greater than 50%. It means the extent of overlapping must be less than 50% to result a stable molecule. Here is another postulate that the electrons that are present in the orbitals must be spinning with the opposite spin, which means this orbital, if has the electronic spin clockwise, then the other orbital must have the anti-clockwise electronic spin. So two electrons in two orbitals must be rotating with the different electronic spin. So this was the fifth postulate. I am writing here, this is the fifth postulate of valence bond theory. So based upon these postulates, now let's talk about how the atomic orbitals s, p, d and f overlap and which kind of overlapping results in sigma and which kind of overlapping results in pi bond. Let's talk about sigma molecular orbital or sigma bond that is formed by the head-on overlap of atomic orbitals. The orbitals sp form the sigma bond. The overlapping of SS, sp and pp overlap results in sigma bond or sigma molecular orbitals. As you know that the electrons are waves which are residing in the orbitals, which means the orbitals are also the regions of waves. So this is the psi 1 or wave function of electron 1 and this is the wave function of electron 2. Both are in phase. You see that both are in phase, so their overlapping will result in bond known as valence bond, and both of these waves when overlap or the superposition of psi 1 and psi 2 result in increased amplitude of wave. This kind of overlapping of waves is known as the constructive interference. So constructive interference of two orbitals or two electronic wave functions results in bond or valence bond. Valence bond or bond wave function contains the increased amplitude of wave. So for the constructive overlapping of atomic orbitals, two atomic orbitals must have their wave function in phase. The constructive interference of atomic orbitals or electronic wave functions result sigma bond by the overlapping of s orbitals, sp orbitals and pp orbitals. You know that s orbital has electronic probability equal everywhere. The probability of finding an electron in an s orbital is same everywhere. So the overlapping of s and s orbitals always result in sigma bond. There is always a head-on overlap in s orbitals. This kind of overlapping is seen in hydrogen molecule. The s orbital of one hydrogen atom overlaps with s orbital of the other hydrogen atom and result in sigma bond. This kind of overlap is ss overlap that is represented here. You know that one s orbital is half filled. So let's say this is the electron in one hydrogen atom that is spinning clockwise, and this is the other electron in other hydrogen atom that is spinning anti-clockwise. So the two orbitals which are half filled, symmetrical, in plane, have same sign and have the electrons which are rotating antagonistic to each other overlap, and this overlapping result in bond. As this overlapping is head-on overlapping, so this bond is a sigma bond. And the overlap is SS overlap. In sigma bond, the electronic density is concentrated about the line joining the two nuclei, and this line that joins the two nuclei in a bond is known as the bond axis or nuclear axis. In a sigma bond, the bonding electrons reside between the two nuclei along the bond axis. Now let's talk about sp overlap. The s orbital can overlap with the p orbital, resulting in sigma bond or sigma molecular orbital. As you know that the p orbital has three degenerate orbitals, px, py and pz, that are differently oriented in space. One of the p orbital, either px, py or pz, overlaps with the s orbital and result in sigma bond. This p orbital is half filled, let's say having the clockwise spin, and s orbital has anti-clockwise spin, so their bonding electron pair has two electrons with opposite spin. This overlap is sp over overlap and bond formed is sigma bond. The examples include hydrogen halides. X can be fluorine, chlorine, bromine and iodine plus ammonia. These have sp overlap. Let's talk about hydrogen fluoride, HF. Hydrogen has electronic configuration 1s1 and fluorine has electronic configuration 1s2, 2s2, 2px, 2py, 2pz. Its atomic number is 9 to 4, 5, 6, 7, 8 and 9. Only 2pz orbital is half filled in fluorine and 1s in hydrogen is also half filled. So let me draw the opposite spin in 2pz. This. So 2pz of fluorine overlaps with 1s1 orbital of hydrogen and result in sp overlap of this kind. Same is the case with hydrogen chloride, hydrogen bromide, hydrogen iodide and ammonia. Compare the bond energy and bond length of hydrogen halides. Hydrogen halides are formed by the sp overlap of atomic orbitals. In HF, 2p orbital of fluorine overlaps with 1s1 orbital. In HCl, chlorine has 3p orbital, HBr 4p orbital of bromine and Hi the 5p orbital of iodine overlaps with the 1s1 orbital. You see that the p orbitals are moving away from the nucleus and a orbital that is away from the nucleus is less influenced by the nucleus. So 2p orbital is greatly affected by the nucleus. Its attraction for the nucleus is greatest. So an electron in 2p orbital when overlaps with an electron in 1s1 orbital of hydrogen, they result in greatest extent of overlapping, and due to the greatest extent of overlapping, the electronic density is more attracted by the both of the nuclei. Due to the greater attraction by the nuclei and the greatest electronegativity of the fluorine, the bond energy of HF is the highest, and the iodine being the least electronegative atom and its 5p orbital being farthest to the nucleus has lowest bond energy. Moreover, HF has the highest bond energy, so its bond length is the lowest, while the Hi has the highest bond length. Now let's talk about the other kind of overlapping known as pp overlap that can also result in sigma bond. Let's say this is the p orbital that overlaps with the other p orbital. Both of the p orbital have same sign and electronic density, electronic spin antagonistic to each other, and both are the half filled. They come close to each other, overlap and result in this molecular orbital known as sigma bond. This kind of overlapping is seen in boron trifluoride, fluorine, chlorine molecule, bromine molecule, iodine molecule, carbon tetrachloride. These all of the molecules have pp overlap. Now the very important point about the sigma bond is every first bond between two atoms is always a sigma bond. So pp overlap will result the sigma bond if this p orbital is the first orbital between the two atoms that will make a bond. If there are 3p orbitals available for the bonding, one p orbital the first bond between the two atoms pp overlap of two atoms will result in sigma bond. The remaining two orbitals will result in pi bond. So very first bond between the two atoms is always a sigma bond. Let's talk about the bonding in boron trifluoride. Bonding in halogens is same. Let's discuss the bonding in boron trifluoride. Boron has electronic configuration 1s2, 2s2, 2p1. While the fluorine has electronic configuration 1s2, 2s2, 2p2, 2py2, 2px2, 2py2 and 2pz1. Here 2pz is the only orbital that is half filled. While you see that one boron atom has only one electron in its outermost shell that is half filled, while it is making three bonds. So here comes another phenomena of excitation. One of the electron in 2s2 is excited to the 2pz, so that there are the three orbitals available that are half filled. So these three orbitals overlap with three fluorine atom and result in BF3 molecule. One of these overlap is sp overlap. Here is the 2pz of boron that is half filled. It overlaps with 2pz orbital of fluorine. This overlap is 2pz overlap and the bond is sigma bond. Two x is perpendicular to 2pz. So this is the perpendicular orbital that will overlap with another fluorine atom and result in a sigma bond. This is the 2px and this is 2pz. So the overlap is 2px, 2pz overlap and the bond form is sigma. The other orbital is s orbital that will overlap with the p orbital of other fluorine atom and result in sp overlap and a sigma bond. So the Lewis dot structure of boron trifluoride is this. One of these is sp overlap and the other are pp overlap, and all of the bond are sigma bonds. Now here is a point that one of the bond in boron trifluoride must be different from the other two bonds. This is the point to be noted. Its answer will be given to you at the end of this video in the limitations of valence bond theory. Now let's talk about the pi molecular orbital or pi bond that is formed by the lateral or sideways overlap. After the formation of one sigma bond between the two orbitals, if p orbitals are available for the bonding, they will not make the sigma bond. However, they will be bonded by the pi bond. Let's say this is a one p orbital that is going to make a bond with the other p orbital. Both are parallel to each other. So they overlap and result in pi bond. Their overlapping is like this, known as sideways overlapping. Their sides are just overlapped, and this extent of overlapping is less than the extent of overlapping in sigma bond. The atomic orbitals overlap such that they are the two regions of overlapping, and both of the regions are above and below the line joining the two nuclei, or above and below the bond axis. So two regions of overlapping in pi bond are above and below the bond axis. In these regions the electronic density is available, so the probability of finding the electron in pi bond is above and below the line joining the two nuclei or bond axis. In the sigma bond, there is only one region of overlapping, while in the pi bond, there are the two regions of overlapping, and this bond is known as the pi bond or pi molecular orbital. That is showing the electronic density or probability of finding the electron above and below the line joining the two nuclei. Let's say this is the p orbital that is half filled with a clockwise spin of electron, and this p orbital is having the anti-clockwise spin of the electron. So they overlap and result in pi bonding. And you see that the electronic density is above or it can be below the bond axis. This electronic density is less attracted by both of the nucleus because of its presence not between the two nuclei but above the bond axis. Therefore, it is less attracted by both of the nuclei and has less energy. Its energy is approximately less than 65 kilocalories per mole. Because of its less energy, it is less stable as compared to the sigma bond. Being less stable and having the less energy, its bond length is greater, so length of pi bond is always greater than the length of the sigma bond. This kind of bonding is seen in nitrogen, oxygen, alkynes, alkenes, etc. Let's discuss the bonding in oxygen. The electronic configuration of oxygen is 1s2, 2s2, 2px, 2py, and 2pz. You see that py and pz are half filled. Py and pz of one oxygen atom overlap with 2py and 2pz half filled atomic orbital of the other oxygen atom, resulting in one sigma bond, one pi bond. First bond between two atoms is always a sigma bond and is formed by the p overlap or 2py overlap. After the sigma bond, the pz orbitals of oxygen are parallel to each other and are half filled. So they overlap literally above and below the bond axis. This is represented by the two lines. So their overlapping is sidewise, resulting in pi bond. So this can be picturized as like this. This is the pi bond between the two oxygen atom, and this is the sigma bond between the two oxygen atom. So one oxygen atom is formed by one pi bond and one sigma bond. The bond length of sigma bond is less while that of the pi bond is greater. Same is the case with nitrogen and alkynes. Let's talk about the bonding in alkynes. This is acetylene, the simplest alkyne. Carbon has electronic configuration 1s2, 2s2, 2px, 2py, 2pz. You see that its 2px and 2py orbitals are half filled while 2pz orbital is empty, which means carbon should make 2 bonds, but actually each of the carbon is making 4 bonds, which means one of the electron in 2s is excited to the 2pz, and the excited state electronic configuration is 1s2, 2s1, 2py1, 2pz1, 2px1. So here are the 4 half-filled atomic orbitals available on carbon atom. So these orbitals overlap and result in 1 sigma and 2 pi bond. First bond is always a sigma bond, remaining bond between the two atoms are the pi bonds. So here is s orbital of one carbon and the s orbital of the other carbon, resulting in sigma bond. After that, each of the carbon is left with let's say these are the two carbon atoms and their s orbitals have overlapped with s orbitals of hydrogen, resulting in this sigma bond. Remaining are the p orbitals. One of the p orbital will overlap and result a sigma bond between the two carbon atoms. Remaining two orbitals are perpendicular to that orbital. So these orbitals sideways overlap and result in pi bond. So there are 2 pi and 1 sigma bond between two carbon atoms in alkynes. This is known as the p-pi bonding. Up till now we have discussed the postulates, the sigma molecular orbital and pi molecular orbital. The p-pi d-pi bonding and d-pi d-pi bonding will be discussed in the next lecture. For now, let's compare the sigma and pi bond. Sigma bond, pi bond. Sigma bond is formed by the head-on overlap, while the pi bond is formed by the sideways overlap. Sigma bond has electronic density between two nuclei or at bond axis, while the electronic density in pi bond is above and below the bond axis. It can be above or below the bond axis. The third point of difference is sigma bond is formed by the SS, SP and PP overlap, while pi bond is formed by the PP, PD and DD overlap. Fourth point of difference is the first bond is always sigma between two atoms, while pi bond forms after sigma bond. Fifth point is only one sigma is possible between two atoms. However, there are multiple pi bonds can exist between two atoms. Sigma bond is a stronger bond, has high energy. Due to high energy, it has lower bond length, while the pi bond is less strong. Because of being less strong, it has less bond energy and greater bond length. Having the high bond energy in a sigma bond, it is a stable bond, while pi bond is comparatively less stable. The examples include for the sigma bond are alkanes, halogens, halogen acids, peroxides, alcohols, ethers. While the examples involving the pi bond are all of the carbonyls, either these are the carboxylic acids, aldehydes, ketones, acetamides, acid halides, acid anhydrides. All of the molecules involving the carbonyl group have the pi bonding. Moreover, nitrogen molecule, oxygen molecule, alkenes, alkynes, these involve the pi bonding. Let's talk about the limitations of valence bond theory. Valence bond theory couldn't justify the bonding in beryllium, boron and carbon. According to VBT, the beryllium cannot make a bond because the 2s orbital of beryllium is completely filled, so it shouldn't take part in bonding. But actually beryllium takes part in bonding. The bonding in boron trifluoride, one of the overlapping is sp overlap, that should be different from the other two kind of the overlapping, so it couldn't explain and justify the bonding in boron, as all of the bonds in boron trifluoride are equivalent. So according to VBT, the one bond must be different from the other two bonds, so it couldn't explain the bonding in boron. Similarly, it couldn't explain the bonding in carbon. According to VBT, carbon must be divalent because it has two half-filled orbitals, but actually is a tetravalent. The concept of excitation was further extended and tried to explain the bonding in carbon, but still the bonding in carbon couldn't be explained because one of the bond in made by carbon, let's say in carbon tetrachloride, must be different because of the different overlapping, but actually all of the bonds in carbon tetrachloride are equivalent. So VBT couldn't justify the bonding in beryllium, boron and carbon. Moreover, it couldn't explain the paramagnetic behavior in oxygen. Oxygen atom, as we have discussed earlier, it is formed by the one sigma bond and one pi bond. All of the bonds are paired. So according to VBT, oxygen shouldn't show the paramagnetism, but actually oxygen is weakly attracted in magnetic field and shows the paramagnetic behavior. So VBT have no reason to explain the paramagnetism in oxygen. VBT couldn't explain the odd bonding. According to VBT, bond is formed by the two half-filled orbitals and they result in completely filled molecular orbital having two bonds in the form of one pair. So what about the bonding that is formed by the three electrons? VBT couldn't explain this. Moreover, it couldn't explain the coordinate covalent bonding where the bond pairs are shared by one orbital only. And lastly, the VBT is highly focused in purely covalent bonding. it couldn't explain the ionic character in the bonding. So these all are the limitations of VBT. In the next lecture we will talk about the p pi, d pi, p by p pi and d pi bonding. So stay tuned, like, share and subscribe to my YouTube channel, and thanks for watching.